So, hi, I'm Nate Stevenson.
I'm Angel.
I'm Matt Koenig.
I'm Jake Connolly.
And we're the smart cloth design for tracking and localization.
So for our mission statement, we wanted to develop a smart cloth that was flexible and it had to be RFID. Of course, we wanted to set up a system where we could localize the antenna. We needed to find its distance and its position. We had a couple constraints, of course, our weight, the radiation, the size, and then the detection distance.
In order to do this, we're using patch antennas. So my patch antenna has 5 parts: the microstrip lead, which is the transmission line that will carry the signal to the patch, which is the conductive surface on the top of the dielectric, the substrate, which is the dielectric material that the patch and lead are attached to, the ground plane, which is the conductive surface on the back of the dielectric that's used to reflect the signal, and then we're using IC chips to impedance match to our reader so that the user can read it. So we chose the ISO 18006 chip because that allows for multiple antennas to be read at the same time. So we'll be able to get a proper setup.
And this is the environment for actually tracking our smart cloth antenna. These tags right here are just bone tags that are passive RFID antennas. This would be like our smart cloth antenna. This would be our reader. And the reader has a view of 180 degrees, meaning like anything behind it, it won't be able to read. And our system of actually trying to localize our smart cloth would involve rotating the reader and tracking the time read for each of these bone tags. And because they each have their own IC chip with their own unique identifier, we can actually know which ones are currently being read. So using which ones are currently being read, we can know the orientation of where the reader is currently pointing. So as it rotates around the room, depending on the time read, so if this bone tag up here was read at say 3 seconds and this one was read at 4 seconds and the smart cloth was read at 3.5 seconds, we know the angle at which the smart cloth is oriented to be in between both of those bone tags. And the last piece of information we need to actually finish localizing its location is the distance which we can get from the RSSI value of the smart cloth. And then using that RSSI value and the power equation, we can calculate its distance by combining it with the actual angle of where it is. We can localize the location of that smart cloth antenna within this environment of like the room with the bone tags.
So we had 2 topologies made, one with denim and felt, which we'll talk about in a second. We chose these 2 specifically, denim and felt, because we needed a better bandwidth. Of course, when there's a bunch of electrical signals in a room, the bandwidth is important because sometimes we can't find our antenna. So denim and of course felt were the best for the bandwidth. Here we have them. We use the software. It's called FICO, which we tested out the antennas. This antenna, they're both running at 920 megahertz. You can go to the next slide. You can see it. And then the permittivity of one is 1.6, and this one is 1.38. We actually have a couple of the iterations of the antenna, which we'll pass out so you guys can look at them. If you guys could please just be careful with them. They do rip easily. As you can see, they're made out of denim, so obviously they're relatively cheaper. That's the goal that we have. We want to make it cost effective. They cost less than $1 depending on how much cloth we end up using. Of course, through miniaturization, we can make these smaller, and then therefore, obviously, difference of weight, difference of flexibility, and then difference of substrates and the materials used. And then, of course, we have the sizes here. You can go back so I can. We have one at 125 millimeters. It's a perfect square, and then the next one is 135 by 135.
So with the ones that we're passing around right now, yeah.
So why is the back so covered?
So the back is it's called the ground plane, and that's what we use to reflect the signal back to the reader itself. And then the patch, and the patch is just what tunes the frequency. Okay. So those ones that we're passing around right now, the conducting material is very like and stuff. copper tape, it's a conductor. So that was just like our original prototypes. We have another material that we're gonna be using our final ones called Shield X Cone, just from a German company, and it's like a pure conductive fabric, so it won't wrinkle like pretty much nearly at all. It's just a sheet of like copper threads bound together. So we'll be able to like directly implement that with very little wrinkling, which just caused like some losses and stuff.
And to implement that, all we have to do is hire it on. So as soon as we get them working at 100%, these are currently working at near the frequency, but not exactly as what we wanted to work with this. So it's not reading currently, but it is. We have proved that they are resonating. They are working near to a gigahertz. We need to drop them down to the required frequency of 920 megahertz. Of course, that could be due to the wrinkling towards the size. Of course, manufacturing these we need to be very detailed with manufacturing antennas. And with these specifically, since they're made out of this material, it's harder for them to work appropriately, especially when we're cutting these with materials that aren't as accurate as we'd like them to be.
So this is basically our current measurements that we taken into account by actually setting up a demo with this reader. So basically we set a long ruler, it's not a meter stick, it's I think 2 meter stick, and we set distances going down half a meter from 1.5 meters all the way down to half of a meter. And we measured the RSSI value of each one. And then the third column would be our calculated distance. So as you can see here, it's not 100% reliable, but there is a very small difference. So for example, 1.5 at the top, we measured a RSSI of -51, and that using the power equation that we reformatted to solve for distance, we got a calculated distance of 1.520 meters. So it's very close. It's not 100% accurate, and that's where we will implement the time to narrow it down even more. So as I talked about before, we have the power equation up at the top right, for the solving for RSSI. We changed that to solve for the distance. Those few other variables that we have there, such as A is our RSSI value that we will be plugging in that we measure. N is the environmental factor of the room. So basically, the more electrical equipment in the room, the more interference you're going to have. So that environmental factor has to be measured beforehand so that you can get an accurate measurement in the space that you're testing. And yeah, we created a program where if you just plug them in to the program, it'll do all the math for you, and then it'll spit out our distances. Here we have a graph, of our line of best fit or our line of regression, saying that the closer the RSSI value gets to 0, the closer the tag is to the reader, and that's exactly the relationship that we wanted to see. So
like, just to dive into that equation a little bit. So the A in that equation is the RSSI at a reference distance. So we took that at 1 meter, just the DBM. So you use that, and then the separate RSSI would be the measured one. And then, so we took a bunch of values so that we could find the environmental loss in the room. So we took like 25 different values so that we could like fine tune what our exponent loss was. So whenever we set this up, we used it in like 3 different rooms. We always take like 25 measurements, like before we give a demo or anything, just so that we could fine tune the exponent loss. And we always take our RSSI reference distance, make that 1 meter, and use whatever it is for that solve for those values.
And on another point for our final design, it's not intended where like if you wanted to use this in the system, you're going to manually be finding all these distances and calculating the environmental factor. Kind of just with the bone tags in the room, since they're going to be known like distances already, you can just do like a calibrate, rescan the room, and it will automatically do like why the progression to calculate the environmental factor. Right now, while we don't have the software, it's just done manually.
And quickly, we have a demonstration for you guys. It's a video. You guys can just watch it for a second, just 2 minutes. this circuit as you can hear me right now, is currently scanning on this monitor at our RSSI values and collecting every part that is stage. So here we have a procedure. We have 6 different positions, starting from 1.5 down to 1.5, then 1 meter, 0.75 meters, 0.5 meters, and lastly 0.25. What we'll do is we'll put a card at each position, and as we'll move down, we'll have the RSSI value that is shown on the monitor. Your name will be saying out loud, or it come down. So that RSSI will be used to calculate distances.
Negative 53 now. Negative 48, yeah. Negative 47, yeah. Negative 40, yeah. Negative 40, yeah. Negative 34, yeah.
But as you can see in our table here, we have the RSSI, the estimated distance, yeah.
You got it. So these are the results from that demonstration that we just saw. So we have the DBM, the measured RSSI on the left, then the estimated distance that our formula created in that room, and then the actual distance. So in our lab, we got a little bit more inaccurate results from when we did from our live demonstration in our senior project at the end of the first semester that you just saw those results on the table. So here we were measuring for 1.5 meters, we were actually measuring due to our DBM of negative 53 and the environmental factor in that lab, 1.89. So still somewhat accurate, but not as accurate as we would like after implementing everything else that we have to do this semester. But we still get that important relationship of as the DBM gets lower, the measured RSSI gets lower, we get closer to the reader, which is that relationship that we still want. So can I go to the next?
Okay. So
Yeah. So that is a that's basically to simulate our smart cloth antennas that were just being passed around. At that time, we didn't have them 100% working, so that was an RFID tag. Yeah, off the shelf RFID tag. Yeah. No. It was passive, so it was just taking that signal in, and it was the RFID reader was actually reading all of it and just sensing where it was.
it would reflect it.
Yes.
It was reflecting back the signal from the RFID tag.
So like the reader would send the signal out, and then the RFID tag would reflect it back. That
Just like a mirror, no batteries.
no,
No.
batteries, it's all passive. Yeah.
Like a chip card.
Yeah.
Yes, it's a passive.
So some practical uses, tracking packages within the warehouse, if they all had RFID tags, like we had the tags stuck around the warehouse, you didn't know where things are at certain times. And then this one, the next one is more focused on the smart cloth aspect. If you would make a smart cloth GPS antenna and then embed that on the clothing for like hikers, if they were to get lost, you'd be able to locate them much easier by just whatever shirt they're wearing that has the smart cloth antenna already embedded onto it. And then prison security. So if you had the RFID locating, like you'd be able to know, let's say you were to set up the boundaries within like a cell, you'd know when they left the cell at like what time they left it at, if they were being tracked with RFID tag, like built into their chunks. Yes.
Why aren't you using time instead of signature?
So we're using both. Our plan is to end up using both so that we can, specifically the time will be for the position. So the RSSI we're using, of course, RSSI isn't the best for this. There are different ways to do it, but they include more money, and of course, it does become more convoluted mathematically. So we wanted to use RSSI because as we tested, it is as accurate as we need it to be. So and of course, if it's in a general area, that's all we needed to be for the specific.
And then additionally, for the just using time, you can't really determine the distance since we only have one reader. It would be possible to like triangulate it with like multiple readers, but within our budgets, like that one reader, it reads up to like 10 meters was about like $250. And they do make longer range ones and a lot cheaper, shorter range ones, but what we needed, we could only afford one reader, which is why we're using DVM data to find the distance of the reader.
And to follow up on the question of biases. When you are in confined spaces, whether it's small spaces, there the time signature is probably harder to track. Correct?
Yeah.
Yes.
Low cost electronics.
Yes.
So how effective, where is the cutoff?
So yeah, that's a really good question. For now, we've been testing a bunch of different, I guess like simulations kind of a thing. Of course, we don't have the exact number for the cutoff region, but whatever that cutoff region is, for example, the prison security example, for cameras, that would work a lot for camera, or well, because for cameras, there's blind spots. And for this, of course, we will have a blind spot because once we get closer, there's that inconsistency. And of course, we can set up the boundary in a way where, for example, let's say it's kind of like attached to a wall, where it's in the wall. And of course, when with these readers, they go 180 degrees, so it won't have to spin all the time, depending on the room. So, of course, with that cutoff frequency in mind, if they are in that range where it's harder for them to scan, we can just it can guess, the algorithm would be able to guess where they are specifically. Them being that close doesn't really change the situation. For example, for the warehouse, the reader could be farther enough from all the anything within the warehouse, so that then it doesn't interfere with the algorithm. Did you want to add to that?
Yeah, so further interview, so you asked like where the cutoff RSSI versus time. So time would be more effective at longer ranges because they're at close ranges, all the times are so similar. They're like milliseconds responses and things, so it's a lot harder to see the difference. And in addition to that, the further away the tag is from the reader, the more inaccurate the RSSI will be anyway. So the further away you get from the reader, the more likely you should be using time to calculate that distance. But because we're only demoing with such a small scale, we haven't had to use time because the RSSI is from the accurate.
Yeah, but just, I'm sorry, I'm curious, short distance and time is probably in nanoseconds.
Yeah, yeah.
So video wave travels so fast.
Yeah.
You're probably working with a microcontroller, which is not people working with nanoseconds.
Yeah. So we have it running through a Raspberry Pi right now.
Yeah. So currently, so there was another issue that we were running into. Of course, if you saw in the video, we were writing down things manually and then plugging them into the equation. There was this whole process. There had to be a middleman between it. So of course, the Raspberry Pi has helped us with that, where we take in the RSSI data that's coming in, and it also takes into account the time. So as the antennas are being read, it puts it into the equation that we formulated, and then it gives us our distance. So for as of now, for again, like Nate said, for the stuff for the what we're trying to simulate, where we're trying to show the proximity to the antenna isn't bothering us too much per se. So what we want right now is to prove two things: that we can locate the position using the one RFID, and that we can create an antenna out of a cheap substrate, for example, denim and felt.
Questions. Can you track more than one target simultaneously with this design?
Yeah. So the chip that we used was as I said earlier, the 18060. They give us like a lot. You can track.
Okay, so it scales to like some.
Yeah, so we like I think it was like the 6B like time. So we chose a chip that would allow us to use as many so like
And then you mentioned that there's interference very close to the antenna with one of the antenna. Your denim is, if it's close to the antenna, it could potentially cause interference. So in your prison scenario, if someone's like locked up against the antenna, is that rate reading the other
So
side.
it's not so much so that it breaks the system, it's just harder for it to, the one that's closer, it's harder for it to tell exactly where it is. It's not as precise.
Yeah.
So that's filtering something.
Yeah, and like, if they were like that close, the RSSI value, like, it would dictate that they're within like, so like, if they're within a foot of it.
So basically, in conclusion, we're trying to develop a system where we are able to transmit an RFID signal to a wearable and wearable passive antenna. So this way we can localize the person into the room, and it needs to have seamless communication between the reader and the person wearing the antenna. This is a growing industry because we are able to enable wireless data exchange between RFID, and it's not really something that's done right now. And there's a lot of research going into it. IEEE has published a few papers on it. It will enhance the capabilities of any wearable smart device if it can be put into a small enough form factor.